Hello, in this video we're going to be talking about Math 3, Unit 3, Day 1. And Day 1 is the beginning of an exploration on polynomial functions. And for students to get an idea of what a polynomial function might look like, we have a variety of exploration options for you. I just wanted to look through some of what is provided so you can make a decision on how you might like to instruct that. And so one of the first things you'll see is something that should be about a 5-minute activity. And it's called a polynomial sorting activity. And here you're given about 12 polynomials, various lengths, various degrees, and students are asked to sort them in a way that makes sense to them into distinct categories with their partner. And I don't like to cut them into little pieces. That is one way you can do it. It is very nice physical activity to rearrange them, but this is not something we're going to come back to again and again like you might have done if you taught Math 1. And so Unit 0, and so I just labeled these with letters so that they could sort them without having to spend the time on cutting and all of that kind of stuff. So the two most common ways that I have seen students sort them is by the number of terms, so 1 term, 2 terms, 3 terms, and 4 terms. The monomials right there, binomials here, trinomials, quadrinomials, all sorted. And then if you're not going to sort by terms, another way you might be able to sort this out is find an alternate way you could sort them and list your explain your rationale. I didn't write down the rationale, but I did I titled them. I didn't write a sentence. And the rationale for this one I had was what was the highest exponent, which we would call the degree. And so here you can see an x to the 4th being the highest exponent gave me L, K, and F, and so on. And there was one with no x's at all. J only had a 3. And so that's the two most common ways to sort. You will undoubtedly have some creative child who wants to make some silly non-predictable rule, but I think that these things will bring out vocabulary that we want to make sure we all agree on as we begin the unit. Now on the back side of this, you'll see a list of vocabulary. I do not think it is important to do a 10-minute or 15-minute lecture where you write down definitions and they're diligently copying these all down. Most of these they've run into in the past. But what you might want to do is say, this is vocabulary we're going to be doing in the unit. You could assign it for homework even the night before after the test. You could assign it to be done by the end of the week if you felt like collecting it. But I probably would choose to use it as just a discussion. Can we just make sure we all know and agree on what all these things are? And anything that we're not really certain on, I'll go ahead and give that definition. So if nobody answers, if I ask you, what do you think a polynomial is, and nobody can answer, maybe we better write down that definition. And usually that gets discussion going in my class. So I'd let them either give a word definition or an example, and then I would probably just say what I thought those things were. The ones I think you will need to make sure that they're clear on is degree. They need to know what the degree is. You might want to double check on term and just make sure they understand that. And then they probably haven't heard cubic or quartic polynomial. So those things you might want to just double check to make sure they know. But I would not spend a big giant chunk of that day just writing down this vocabulary. That's not the most important thing of this lesson at all. Next thing you'll find in your folder as something for you to use, this is teacher instructions, and I actually took this part of the teacher instructions and I just copied and pasted and made a worksheet to give out to my students so that I could have them write on it. But it would be just as nice to project that on the board and be able to just draw right onto the board in these boxes as part of a class discussion. I could take it this way and cut and paste it into a document or use it to project under my DocCam and get them to do that. So the idea of either of these is just kind of a tying. We talked about polynomials, we figured out ways to sort them, we talked about vocabulary, but now we've spent the whole last 2 chapters graphing things. What does a polynomial look like? What is a polynomial graph? And so here are some different kinds of functions we've learned before. A constant function, and they could just make up anything they want here and graph that. These don't have to be perfect graphs. A linear function, let's keep life simple, y equals x minus 1 and up 1 over 1, and that would be a wonderful linear function. If you would prefer to have them write f of x, that's really totally up to you. Absolute value of x minus 2, and they should be, after our discussion of shifts, they should be really good at graphing these after the last 2 chapters. That's an absolute value function and a quadratic function. Again, keeping things really simple, x squared plus 1. And so I'll go up 1, put that vertex, and then I'll go up 1 over 1, up 1, back 1, up 3 over 1, up 3, back 1, and get a really rough parabola there. So these are functions they should know. This is a little review. Again, having them do that with their groups or come up to the board and draw one, that's fine. So the question is, what we don't know is polynomials. We just did all that sorting of polynomials. What do those graphs look like if we try to graph one of those? But actually, they do know some polynomials. Some of these are polynomials. As a matter of fact, all of these are polynomials except for the absolute value function. And anything with a sharp turn is not going to be a polynomial, but all these nice smooth turning functions are polynomials. This one is a monomial. And so they should have everything except the absolute value is a polynomial. And then this is a question right here that really is important and motivates our lesson. What features that we sorted by change the way a polynomial will look when graphed? And one of the things we sorted by was the degree, or the highest power of x. And we can see that when x is squared, it looks entirely different than when x is to the first power. And so I don't know if we know anything about number of terms and how that changes how things look, but definitely degree does. And so they should guess that degree someone might come up with a negative sign, because we know that when there's a negative in front of the highest power, that makes our parabola upside down, so in front of the lead coefficient. And so they might also think of that as something that changes a graph, because we know negative f of x reflects across the x-axis. And so those would be 2 things I would think that they might be suspicious of. If you don't get those things, especially the degree, you're going to want to fish for that, because that's really what we're going to explore. And so you would like them to come up with, like, hey, I think maybe it could be the degree. And so that motivates our exploration. So that's a second thing that you have as an option. Remember, this was the same thing, just in a different form, a teacher form. This is just kind of the discussion that I would have, and we just did that together. And then on the back of that, the second page of that document, it gives a couple different options for how you can proceed with an exploration. So you might have students explore in pairs, or you might lead a class exploration. So options for graphing: you could use a graphing calculator and project some graphs, or you could have students use Desmos on their phone and be able to graph things. You could put Desmos on your computer and project that. There's lots of different options that you might have. I don't think myself I would make the decision of walking to the computer center to do this, because it's too short an activity. I would lose too much class time for the walking back and forth myself. But if you have computers that you could just have accessible in your room, you could do this with computers. And so here's two different options. There is this nice activity right here, which is what I'm going to go through next, about polynomial and behavior exploration. These extra equations on this one are really here for you. I spent some time finding equations that if I type it into a graphing calculator, these equations fit on the standard screen without me having to adjust the window. And I wanted to have those there for you just in case one of your students was saying, what happens if you have a 5th degree equation, or what happens if you have a 6th degree equation, or what happens if you have a lot of terms, or and you wanted to be able to show them, answer that question by giving them an example. I wanted to have things I know that you could graph and they would fit easily on this graphing calculator screen. If you're using Desmos, it's not really that much of a problem, because it's very easy to change the screen from graph to graph without any trouble, and I'll be showing you that in a minute. So these I didn't necessarily mean you needed to use. It takes a while to type these in with all the terms and exponents, and so if you're going to use some of these, you'll want to prepare by typing them into the calculator in advance, or the computer in advance. It's very easy to do. And once you do it, especially on Desmos, once you do that, you can save that graph and use it again next year and just pull that up as a document. So you can even save it to your Google Docs and have it there next year. So it's great. You don't even have to find it in a big long list of graphs you've done. All right, so I'm right now going to look at this one, and I will show you if I was projecting from a graphing calculator. I'll show you how that would look first. If I was having students do it, it's going to take about double the time, but there is something kind of cool about having them put their hands right on a graphing calculator if you have a class set and they don't have a lot of exposure to that. So I'm going to turn on my graphing calculator, and as a teacher, since I was going to demo this, I actually went through this entire worksheet and I entered all the equations I was going to need here in my y equals. All these three that are darkened right here are all from number 1, and then if you go down you'll see the ones from number 2, and so on. Now if you enter them all and you don't want them all to show up at the same time, then what you do is go sideways over onto the equal sign, you hit enter, and that will turn off or on any function that you want to show. So right now, with them all turned off, if I hit graph, nothing will show up. And so then if I wanted to turn this one on only, I would hit graph, and there it is. If I wanted to turn on the other two also, maybe put all 3 on at once. Okay, there's the first one. There's the second one, it's a little skinnier. And there's a third one, it's almost on top of that other one. Now if I was really going to use a graphing calculator, I might like to adjust my window to be able to see that graph better. I played with it a lot, and here's a window that I thought was okay. I tried -3 to 3 for this one, and for the y's I wanted a little height still to be able to see the difference between the x to the 4th and the x to the 6th. So I have -3 to 3 for the x's and -6 to 6 for the y's. And that is my x squared. The next one that graphs is my x to the 4th, and then my x to the 6th. I'll still tell you I like Desmos a lot better, and I want to show you that in just a minute. But it is possible to pre-prep your whole presentation by putting them all in and then turning the equations off and on real quickly. So, so anyway, that's how that would go. And then what I would want my students to do after they saw those, they're just doing a really rough sketch. They do not have to do an accurate graph at all. And so here was my x squared. My x to the 4th was a little narrower. Also, if you look at it carefully, it gets a little flatter at the bottom. And my x to the 6th was even narrower. It's nice at some point, if you have time, to ask the kids, oh, that's supposed to be narrower. I like to ask the kids why. Why is it narrower? And have them think about, well, if I'm plugging in the y value of 2, for instance, into each one of these, what's happening with that? And so 2 to the 6th is really high, and so that's a lot narrower as that goes. Good to think about that. Instead of just memorizing something's narrower or whatever. So now I want to show you how you could run the rest of this activity on Desmos. You get the idea for the graphing calculator, and I think you might have less experience with Desmos, and I'd like to show you how that works. So I'm going to set this aside and show you a screenshot of my computer right now. Okay, so here we are on my computer screen, and I want to show you how to work this with Desmos. So if I've been to Desmos recently, so I actually have an icon there, but if you will just type Desmos in your search engine, you will find yourself landing here, the very first one, and right here it says Launch Calculator. So I'm going to click that. And now I'm on the free graphing calculator, and I could do anything I want right now, but I want to show you how to make a graph that you can save and use for later. And so if you forget any of this, I just want to remind you that right up in here is a help center that I've found really wonderful. I've been able to figure out just about everything that I need on Desmos just with this help center. And how I remembered to do this was I went to my help center right here, and I wanted to be able to save a graph to Google Drive. Now this saves the image of a graph. If you save that, you'll have a graph that is not interactive. It's just a picture of it. But if you want a graph that you can work, add to, change the size on, move around on, you want to save your graph. I chose to save it to Google Docs, and that seems to be the one that works the best for me. So you want to save that, and when you click this, it'll tell you exactly how to do that. But I'm going to show you that now. I just wanted to show you that that is the Help Center and how it can work for you. So the first thing I want to do is to show you how to make a graph. So I'm just going to type in an equation. I might type in x plus 2. Sorry, I got x equal to, I forgot to shift, x plus 2. And I used my keyboard, but I could have pointed to these down here and that would have worked fine. I just realized I forgot y equals. And so I'm going to go back here and I'm going to add in y equals. I could be typing this with my keyboard, but I'm just showing you that I could also use this entry pad there. And so now I have this graph. Now, if this was all I wanted and I wanted to be able to save this graph, then I go right up here to this untitled graph. And there's two different ways you can save. You can just save it on this page, but if you're going to make a graph the night before that you want to use later, then to save it, you might want to save it into your Google Docs. So I'm going to click, and it gives me an option to sign in. If you don't have an account, you would make an account. And if I use this lower one using my email address and sign in, then it will not save to my Google Drive. So I'm going to do this. You have to be signed into your Google Drive on Google, and I'll just link using the Google Drive, and I'm going to choose this account right here. I have more than one. I have one with my CUSD, but the one that's Clovis USD.K12, all that stuff, that is the one that gets you to the curriculum guides, and so that's where I'm going to have this saved, is in there. When I want to save this graph, then I'm going to check send a copy to Google Drive, and I will save this as practice graph. And now I'm going to go ahead and save it. And it's saved. It's saved in a couple places, I believe. Let me see if I'm right. Yes, it's saved right here. I clicked these 3 bars. It's saved right here. If I decided I didn't want it, I made an earlier one. I don't want that earlier one. I can just click that X and it'll go away. It gives me a sec to undo that in case I want to change my mind, but notice that that's gone now. And there's this other practice graph here too. There are some graphs that are built in. So there's only 2 with X's here, ones that I've made. These ones are built in by Desmos and things you could use to demo. So now I want to show you where that graph went that I saved. So I'm going to go to my Google Drive. Oops, sorry, let me just show you what the whole drive looks like. I made a folder called Desmos Graphs. When I look in there, I'm not going to see the one I just saved because it always just saves to the bottom, not into any particular folder. So I'm going to go ahead and move this into my Desmos Graphs folder. There it is. And then I'm going to open that Desmos Graphs folder, and I see my practice graph that I just made. And what I'll get is a link to that web page. So actually, if I close the web page I was on a minute ago, it's gone. When I use this link, it'll open a new web page and it'll give me that. If I hadn't closed it, I would see 2 of the exact same thing. And I'm back to this graph. And so this is a great way you can use this to preset things up. Now I've preset up already the entire lesson. So I'm going to go back to my Google Drive and I want to close this one that I didn't really want to be in. This is the one I want to show you today and how that can work. So I'm going to use that. There's a link. It'll open another page up here. Notice. And now I have all of the equations typed in for that entire polynomial in behavior exploration. So the first 3 that we just did earlier are right here. We just did those on the graphing calculator, and I can see those. If I want to resize this screen, zoom in or zoom out, these plus keys will do that. Now I might need to slide the graph up to be able to see what I want to see. Because I have a yoga, so I have a touch screen. I actually, right now, I'm going to pinch this screen, and I can do just like you would on your smartphone and make things bigger or smaller by touch. But if you don't have that, then what you're going to be using is these plus and minus keys to get those in. And those are the first 3 graphs that we compared using the graphing calculator. I like that they're in color. If you're going to be projecting this, instead of having the kids do it, then over here in graph settings, see this tool that I'm at? I'm going to click this, and I'm going to click projector mode, and it just makes everything a little darker so it stands up better. It's also a place where you can set to a specific window if you would like. And there's some other things you can do. I want to get out of that now. Go away. Good. And so those are the first 3. So the next question on that, I'm going to turn these 3 off. And the next question asked us to graph 3 equations that had negative signs, but they still had even exponents. And I can't quite see that. Let me slide that up. And I can see that they're pretty much the same graph, but now they are all starting low and ending low. So that's what happened with that negative sign. That's what we would have predicted from our earlier chapter's work. So number 3 asked to contrast and compare the graphs of the function in problem 1 and 2. And so I would talk about when we had a positive leading coefficient and an even exponent, they started high and ended high. When we had a negative leading coefficient and an even exponent, they started low and ended low. Something like that. They might notice other things. It'd be interesting. So when you've finished answering question number 3, giving them time to write about that, asking them what they came up with, the next one, problem 4, gives us the next 3 equations with odd exponents. And so you might ask the students to predict before you reveal these, but these are the next 3 that they asked them to write. I'm going to move this down, and I'm going to zoom in just a tiny bit. So notice I have a pretty zoomed in graph. I'm just at -4 or 4 and -4. And these are 3 odd functions with positive lead coefficients. They start low and end high. And that would be number 4. They would have to draw those down really quick if you want to show them one at a time. There's the first one, the x to the 3rd. And then here's the x to the 5th. And then here's the x to the 7th. So it's your choice how you like to model those. And then on number 5, it goes on to the odd exponents. And they should see that these graphs are the same graph, but reflected across the x-axis, which is what they learn negative signs do in function shifts. And so these odd functions are starting high and ending low. And so 4, 5, and 6, we just talked about that. Notice you would be giving your students time to write and draw, but it goes really quickly, this exploration as a demo with things pre-typed in. It's a lot slower when you give the kids time to type things in themselves, but it's good experience for them with the calculator and the typing and things like that. So 7, 8, 9, those problems aren't necessary for the kids to get to. So judge your time accordingly if you have time. Students might just wonder what happens when there are extra terms, because so far we've done all monomials. And so those problems are there for that question. But we've got what we need for the lesson now. So what you'll see is with these 2 terms, we now have something that was even. It still started high and ended high. So the degree of the highest term is the one that was making the decision. This one does cross the x-axis and come back, where all the other evens, like the monomials, they were all in the positive. So this little piece of subtraction is making the graph a little bit lower. It's also shifted with the vertex not right on the y-axis. And so there's lots of things we can talk about later. What we'll really be finding out later is about the x-intercepts, but they probably are not going to notice anything about that now. If we add another graph, this x to the 4th has some interesting stuff going on, and here's a more wild and crazy x to the 4th. I think I want to make that bigger so they can see better, and I'll turn off this squared. So these are both x to the 4ths with an extra term. It's a binomial, and so they don't all look just like a perfect W. Some of them are kind of asymmetrical. And so it gives them a chance to explore. When we throw the negative in there, notice these were all even exponents. They all still started high and ended high. And when we throw in a negative exponent, let me turn off the a negative lead coefficient. Turn off those positive. We still see them all starting low and ending low. But again, more wiggling around. Not just with vertices on the y-axis. And then if they go on and check out the odd lead coefficients, the odd degree, pardon me, where are we at? There we go. There's odd degree. This one has a positive lead coefficient, odd degree, starts low and high. This one has a positive lead coefficient, odd degree, started low. I need to make this bigger so I can see the whole thing. I'm sorry, make it smaller so I can see the whole thing. There you go. Started low, came up, had a maximum, came down, and then back up, ended high. And then this one with a negative, you might have them predict, And hopefully they'll predict that this will start high and end low. And in fact, it did. And so you can work your way through this exploration relatively quickly with a little pre-preparation. And then because I saved that to my Google Doc, that document will be there for me next year when I want to teach this again, or next period when I want to teach it again. And all I have to do is turn off the graphs and have a clean slate and be able to start again for third period or whenever your next class is. So all that work is very nicely done. All right, after you've done that, then there's some questions to answer. I'm going to leave my computer screen and we'll look at that together. Okay, and so after you have explored all those graphs, your students should be able to answer these questions relatively easily. What happens when the lead coefficient changes sign? Students should notice that that reflects the graph over the x-axis. They might say that the end behavior switches, or it changes from starting high to starting low, or something like that. There's lots of different ways they might say that, but it reflects over the x-axis is an easy and concise way to say that. What happens when the degree changes? I'm going to tell you that my students felt like the 12 and 13 had the exact same answer. So it's possible if you wanted to edit out one of the two questions, I probably would edit out 12, it's more vague. But my students, I think when we wrote the question originally, what happens when the degree changes, we expected something like the end behavior changes, or as the degree changes from odd to even, end behavior changes, something like that. Now we wanted here, in case they hadn't hit the odd and even thing, we wanted something specific here. And what they really should notice is that odd functions are going to either start low and end high, or they're going to start high and end low. So this would happen if it was a positive odd, and this would happen if it was a negative odd. And they should be able to write some words to say that. They shouldn't just summarize like that. But the end behavior is opposite on an odd function. On an even function, the end behavior is the same, and a positive even is going to be up, up, and a negative even is going to be down, down. And so that would be how that would go. Does the degree have anything to do with the number of real zeros? So looking back, if your students answered those int questions, numbers 7 through 9, they might be able to check those graphs and figure that out. It didn't look like it really did have much to do with the number of zeros. You should see, if you look back at what you did on 7 through 9, that sometimes the third degree, the thing with 3 terms, sorry, the trinomial, has only 1 zero, sometimes it has 3, lots of different things happen. And so this one, so far, they shouldn't really be able to tell. Actually, it happens that the maximum number of zeros is equal to the degree, but it doesn't have to be. There can be less zeros than that. That's just the maximum. All right. And after that worksheet, then there's a nice classroom discussion problem set, and that's really a nice way to make sure that your students really have discovered what you were hoping they discovered throughout this activity. I gave my students a little time to discuss this with their partner, and then I called on them as partners to reduce the stress level. I would say, Joe and Alex, what did you get for the end behavior for letter A? And they would tell me it started low and it ended high. I would like at first for them to be more specific, like as x heads toward the negatives, negative infinity, y also heads toward negative infinity. As x head toward positive infinity, y also heads toward positive infinity. Because I want them to realize that there's two things getting bigger here. In fact, on this one, x is getting smaller as y gets bigger. And so it's not always just increasing or whatever, because you need to be specific about whether it's x or y. So on this one, the end behavior was low and then high. It should be odd degree function because they have different end behaviors, and the number of real zeros are 1, 2, 3 of them. On this second one, the end behavior is up and up. The function should be even because they have the same end behavior, and there are only 1, 2 real zeros. And this last one, the end behavior is down, down, because that's on this side. As x gets more and more negative, y gets more and more negative. As x gets more and more positive, y gets more and more negative. Because those were the same, this would be an even function, and there were 1, 2, 3, 4 real zeros. And so they're just learning to look at the graph, use the vocabulary, and find what they see. What they're going to do with all of this, at the end, here's the homework assignment that we're wanting them to be able to accomplish. So they're going to identify the leading coefficient, 5, the degree, 2, and the end behavior. And they need to know that since it's even, since the function is even, and the leading coefficient is positive, we expect this to start high and end high. As x goes to negative infinity, y is going to positive infinity. As x goes to positive infinity, y is going to positive infinity. So start high, end high. Up, up, you might have them put. And that's what they're doing on all these. I do want to point out that there are a couple here where things are out of order. The x to the 4th here, this should be the leading coefficient, and the degree is 4 and not 3 here. So students need to really be aware, make sure what they're looking at. The leading coefficient is 7, and the degree is 4. It's not just the first term, it's the first term when it's in descending order. And these are just in reverse. You identify the end behavior and then you justify, and your justification should say something about the leading coefficient and the degree. So I would say the end behavior on this should be low, starts low, ends high, and the reason is it has an odd degree and the leading coefficient is positive. Because an odd degree will go 2 different ways, and the leading coefficient being positive means it will start low and end high. Somebody said to me that the sign of the leading coefficient is always matches the second arrow, and that is a good way to remember. In this next part, now from the graph, they're going to say, okay, this degree would be odd or even. This would be odd because it's going 2 different directions, and the leading coefficient should be positive because it is starting low and ending high, ending positive. And then you need to justify that, and so I would say because, exactly the same things I just said, because its end behaviors don't match, and because it's starting low and ending high. So I want to justify with what I saw in the graph. And that's what's supposed to be happening in all of these. This page didn't print well. By the time you use this, hopefully we'll fix this, but make sure you double check it before you run it off. This should be on the front of the next page. It says write a polynomial function with end behavior of, on the left, f of x goes to positive infinity, and on the right, f of x goes to negative infinity. So I see the end behavior is different. I need to write an odd function. And I want the right, on the left, I want it to be going up, and on the right, I want it to be going down. So I need a negative odd. So you can have it be any negative odd you want. So negative x to the 5th minus 17x squared plus 81, whatever numbers you want to pick. What was really important about that was this and this. This needed to be odd, this needed to be negative. After that, I don't really care what they put. So they have a couple like this, and throughout this unit, I found when I did this with my class that some of the end problems were really excellent discussion questions as they came back. I want to encourage you to not give those moments away at the end of class, but let kids come up on those and have a talk about them as they come back. Because for this one, it said, here's the equation of the function and here's the graph. Write an equation for the translation of f of x that has no x-intercepts. If not possible, explain why. So a translation means we're going to slide it up or down or to the right or left, and I think sliding it to the right or the left we can see is not going to change those intercepts. Sliding down, I'm still going to have 2 intercepts. I want no x-intercepts, means I'm going to need to slide it so I get this spot up above that axis. So it's somehow way up here. I want to slide it up. And so since this is just about at -4, I feel if I would add 4, remember we learned that if we did f of x plus 4, that would shift the graph up 4. So the function that I'm looking for, I just need to add 4 to this function right here. So a new function that would shift it up would be this, x to the 4th plus x to the 3rd minus 2x squared. And now I'm going to combine these two like terms, and I will have plus, actually, 4 might put it right on the line. I'm not really sure. I think I'll add 5 just in case. I'll go ahead and shift it up 5. And so notice somebody else might decide to shift it up 10 or 100. So when I combine like terms, I'll have a plus 4. And this function should shift that graph up. I think on my students I had them label this f of x, and I said label your new function g of x. So instead of having that strange label right there, I just called it g of x, my shifted function. Okay, so that's your choice. This problem was really interesting because now it said translate it so it has no x-intercepts, and if you think about this odd function right here, no matter how you slide it up or down, you're going to still have an x-intercept, because no matter how far I slide this keeps going down. And again, if I slide it down, this one keeps going up. So this one is not possible, and they need to explain why. And they should be able to come to a conclusion during discussion the next day in class. Or somebody might like to make a conjecture that every odd function will have at least one x-intercept. There's no way to get rid of them all. An even function doesn't have to have an x-intercept. And so that's actually why that when you use quadratic formula on a quadratic, sometimes you'll get no solutions because it doesn't have any x-intercepts. So anyway, that's the end of the first day, and I hope we've given you enough resources to be able to do a nice exploration, let your kids discover some things, and get excited about this unit. Thanks.